1 and epsilon t minus 1 plus this term index is t and t minus 2 0 plus this is also 0. So this is in the simplified form, this become theta time covariance of the terms with same index is equal to variance, and that is equal to sigma square. Now look what happened to the MA model. The first property is zero mean, this is satisfied. Second property is constant variance, that is also satisfied. Third property of the white noise is no autocovariance, but here is covariance. There is something theta sigma square which is non-zero. So this means this is not white noise. But if you look at the stationarity, stationarity requires the covariance to be independent of time. There should be no t. So if you look, there is no t. So the property of stationarity is satisfied, but the property of white noise is not. So what is the conclusion? MA model is not white noise, yet it is stationary. But what we have done, we actually did this exercise for MA1. If you have MA2, you can repeat same kind of exercise, and if you have MA3, you can do the analysis for any larger leg. But regardless of the number of legs, you will find the MA model is stationary, but it is not white noise. Okay, so this was about MA type of models. Your good name? Naila, are you getting? If you are not understanding any point, you can ask. So far it is going fine. Now we will discuss what about the stationarity of AR models. That is very important. See, this is AR model. Yt equal rho yt minus 1 plus epsilon t. This is your AR model. This model can be expanded. How? This is equal to rho times, if I put value of this on the same basis, it will become rho yt minus 2 plus epsilon t minus 1 plus epsilon t. This is equal to rho square yt minus 2 plus rho epsilon t minus 1 plus epsilon t. So it was an AR model. Now you have converted this into ARMA. There is MA leg as well. you have the past values of epsilon t. And this can be expanded further. I can write the value of yt minus 2. So if you write here rho square into rho yt minus 3 plus epsilon t minus 2 plus these two terms, rho epsilon t minus 1 plus epsilon t. So this has become equal to rho cube yt minus 3 plus rho square epsilon t minus 2 plus rho epsilon t minus 1 plus epsilon t. And you can expand in this way up to the end. If you increase in similar way, here you will have next time, this was rho, then rho square, then rho cube. Next time it will become rho 4. And going in this way, ultimately you will find rho power t y power t minus t is equal to 0 plus rho power t minus 1 epsilon 1 plus rho power t minus 2 epsilon 2 plus up to so on, and the last term would be these two, rho epsilon t minus 1 plus epsilon t. Now after this expansion, I can determine whether this is stationary or not. So how can I determine? I have to check three properties: expected of yt, and then variance of yt, and then covariance of yt and yt minus 1. So let me see what happens with expected of yt is equal to, I can write the yt in this form, and then I can put the expectation on this. This will become equal to expected of rho power t y naught plus rho power t minus 1 epsilon 1 plus rho power t minus 2 epsilon 2 plus up to so on, and at the end you will have epsilon t. So if you assume if y naught is equal to 0, then this will become 0, and the expectation of all other terms is already 0. We have epsilon t is white nice, so expected of epsilon 1 is 0, expected of epsilon 2 is 0, expected of epsilon n is 0. So expectation of all of these terms is 0. If you assume that expected of y naught is also 0, this will become equal to 0. So if expected of y naught initial observation is equal to 0, then expected of yt is equal to 0. This is confirmed. First property is matching. What about the second property? See, second property is variance of yt. This will become equal to variance of all these terms, rho power t y naught plus rho power t minus 1 epsilon 1 plus up to so on, rho epsilon t minus 1 plus epsilon t. So what happens when you apply the variance on a sum? It becomes variance of first plus variance of second plus variance of third plus covariance terms. This is equal to variance of rho power t y naught plus rho power plus variance of rho power t minus 1 epsilon 1 plus up to so on variance of rho epsilon t minus 1 plus variance of epsilon t. As I have said you, expected of epsilon t is equal to, variance of epsilon t is equal to 0. Variance of epsilon t is equal to sigma square. Okay. At end of this, you will have plus covariance terms. Okay. This will become equal to, now again, if you have variance applied on ax, this is equal to a square variance of x. This is the property in statistics, right? If you apply this logic here, it will become equal to rho power 2t variance of y naught plus rho power 2t minus 2 variance of epsilon 1 plus rho power 2t minus 4 variance of epsilon 2 plus up to so on. इस पे अप्लाई करेंगे तो यू विल गेट रो स्क्वायर वेरिएंस ऑफ एप्सिलॉन t minus 1 plus last term will become variance of epsilon t. And I have said you, suppose हम यहाँ पे again suppose